All right. Any questions over the homework? Wow. Definitely need the cricket sound now. Rena. 98? 94. Oh! I remember that one. I was working on that with somebody yesterday. Yeah. Yeah, this is definitely a big challenge problem. So let's go through this one. So you're given the equation of the ellipse, and you're trying to show that the area is that using what we learned. And so the one thing you got to remember, I mean, there's a few things you got to remember, is what this graph looks like. So remember, this is the standard form for an ellipse. Below the x squared, that tells you how far left and right to go from the center. And then below the y squared tells you how far up and down to go from the center. So we go left and right, A units, and up and down B units from the center. So that's just something that, yeah, you are expected to remember that from previous years. So here's the graph of the ellipse. And then we want to find the area. Now, you could just look at the whole area, do top minus bottom, like the whole thing, go from negative A to A. But there was no symmetry in this picture, so I opted, you didn't have to, I opted to just look at the yellow shaded part and then multiply by 4. So that's all I'm looking at. So the first thing, though, it also, and this problem really doesn't matter, it's equally as good or bad, depending on your perspective, if you make it a dx or dy problem. So I chose dx just because that's what we're familiar with more. So I solved for y. So solving for y, you get this. And let's see where I went from there. Oh, and then I kept going with it. So solving for y, you get this. But you can pull out a b squared over a squared, which means you can pull out a b over a outside of the radical and be left with this. So just any question solving for y. And then, excuse me, just like we saw last time, we got that plus or minus. So the positive part is going to be the top part of the ellipse, and the negative part will be the bottom part of the ellipse. So I'm actually just going to look, because I'm only looking at the area of the yellow shaded region, I'm just going to look at the positive one. So the area is top minus bottom. Top is the ellipse. Bottom is just the x-axis, so it's like subtracting 0. And I'm going from 0 to a, multiplying by 4. So any questions setting up the integral? Then there's the solving the integral, which that is not so friendly either. First of all, b over a, that's a constant. So I can factor out the constant from the integral and put it here and just be left with that. But still, how do we integrate this? And there actually is a way to integrate this. We haven't learned it. It's actually not even officially a BC topic. I teach it. It's one of the extra topics I add into BC. So even though at first glance it doesn't look like it would be that bad, it actually is pretty messy to integrate this one. But be prepared. I have seen them do this on the AP. And be prepared just with other calculus classes, because professors love this. This actually is a semicircle. If you recognize that that's a semicircle, you can just use area. Remember, a definite integral represents area under the curve. So that's a semicircle. And actually, to convince you it's a semicircle, unless I don't have this part out, if I have y equals the square root of a squared minus x squared, square both sides, add x squared onto both sides, and it's a semicircle with a radius of a. So I drew a semicircle. And the reason I'm only shading in this part of the circle is because the integral only goes from 0 to a. So the integral is only looking at the area from 0 to a. So this integral represents the area of a quarter of a circle. And so that's what I did to evaluate the integral. So this integral is 1/4 the area of the circle. We're almost there now. But any questions on that? So let's put all the pieces together. So remember we had this integral for the area of the ellipse, but now we know that this part is just 1/4 the area of a circle, and then when you simplify all that, you get pi AB. Ta-da! Yay! Any questions? Godzilla! All right. Any other questions? Godzilla again. I know you guys are just so like, this is so cool. You're speechless. I see the looks on your faces. I can see through the mask. Yeah. All right. Well, if that wasn't cool enough, guess what's coming? Reality check. Yeah, I'm going to pause the video here. There is number 1. Let me scroll up so we can see it all. Now, this is one of those where, because I did this one with no calculator. So to get the graph, I don't know if that's what the graph looks like, but I don't really care. Here, actually, let me scroll down just a bit so we can see the equations. The important part is that y equals x times e to the negative x squared. Well, e being a positive base, you raise that to any power, it's going to be positive. The problem tells us to only go between 0 and 1 on the x-axis when x is positive. So for y equals x e to the negative x, it's a positive times a positive. I know that graph is positive. That's all that mattered. And when x is 0, I know it's going to go through the origin. So that was easy. I just went ahead and put that in there. But then I just made it squiggly. I don't know. But I'm sure that is not what the graph looks like, actually. But doesn't matter. But that's the area. And so then that helped me set up the integral. Now you could have used the calculator to evaluate it, but then you'd have to also evaluate each of the answer choices to see which decimal is equivalent. And that could work. But if you don't already have the hang of U substitution, if you keep on practicing it, I really think this is faster doing this one by hand than trying to evaluate every single answer choice. So, but anyway, there it is. So any questions about that? Anybody want more time looking at it? All right, then here is number 2. And again, this one, you kind of have to make the judgment call on points of intersection. I did the points of intersection by hand. We could have done that feature on the calculator. Honestly, this one's probably a toss-up of which one's faster, calculator. Because once you get the hang of the calculator and finding points of intersection, it is super fast on the calculator. But you got to type everything in. You're going to type everything in anyway eventually. So, yeah, no, it's a toss-up. But I will say this. Be prepared. The AP exam will expect you to be able to do something like this one by hand. So, make sure that you know how to find the points of intersection by hand. But any questions on this one? And just another thing that I want to point out, I don't know how many of you guys did it. I'm guessing probably most of you did, just because you probably, if you're going to use a calculator at all, you probably went to y equals first to put the equations in, to graph it. But make use of the fact that you've got the equations entered in. So I went ahead and just put both of these in already. There's y1 is the parabola, y2 is the line. Now going back to the problem, we can see that top minus bottom is going to be the line minus the parabola. But when you're setting up that definite integral on the calculator, don't try to type in the equations in here. Make use of the fact that they're in y1 and y2. And if you're like, I get flustered. I don't remember where the y's are, and so it's just easier to type it all in. Get used to it. That'll speed things up a lot. And again, on the AP exam, you'll be able to make use of that in a lot of different ways. Now that we're going to start using the calculator a lot more, like I'll show you all sorts of different things that you'll be able to do that will just help things. So make use of the fact you got those equations in there. And then the other thing that I just want to show you, you get this answer. So remember, if you hit math, that first choice says change to fraction. And it will give you the fraction for you nice and easy. So you don't have to, again, evaluate every single question or answer choice. So any questions on that? Either the problem or the calculator. I'll go back to the problem. All right, and then there is number 3. Now, one thing I want to point out with number 3. Oh, I have a silly. Anybody see the silly mistake? The answer is right. There we go. I heard it. Yeah. My integral. I put dx instead of dy. Let me change that. dy. On the calculator, these calculators they're called function calculators. And actually, let me go back to the calculator. How you get the graph is by literally clicking on the y equals button. You always have to solve for y to get the graph. So you can't put in, what was it? 36 minus y squared. You can't do something like, because I see students try to do this. I'll clear and clear. Actually, I should have left those. Oh well. But I see students try to do x. There is actually an equals, but I forget where it is. Is it here? Second math. Oh yeah, because it's test. X equals 36 minus y squared. I mean, I got the equation in there, right? And then I try to hit graph, and it's like, what the hell are you doing? Look at what it says. It says y equals x equals 36. But that makes no sense. That's ludicrous. So you will have to know a little bit by yourself. Now, once you set up the integral, though, you can still use the calculator to evaluate this. And there's 2 things you can do, and it's kind of up to you. When you math 9 to get the integral, you can go ahead and do alpha y and get y's all across the board. But you can use any variable you want. So you still, when you type in this definite integral, you can make all the y's an x just because we have that easy x button to press. It will work. You could, if you really wanted to, you can make all these y's an a, and that's fine. As long as this dy matches whatever variable you're using there. So that's okay. You just won't be able to graph. You won't be able to get this graph. Now, the one thing you could do, because you can do this, let's say we start with x equals 36 minus y squared, and you're like, well, I know it's got to be solved for y, so I'll solve for y. So y squared is 36 minus x. So y is plus or minus the square root of 36 minus x. So you can then do this. I forgot what it was. 36 minus x. You have to enter it in twice, though. So there's the positive square root 36 minus x, and then the negative square root 36 minus x. And I'll zoom out. Well, actually, here we'll just do window. You can get the sideways parabola that way, but it is graphing in 2 parts because it's a function calculator. This is not a function, but each half of it represents a function. So you could do it that way and get your graph that way, but then to evaluate the integral, you won't be able to use y1 and y2 in your integral. Just watch out for that. Does that make sense? Any questions about that? Yeah.
The way I did it, I knew the area would be the same if it was a function where it was like vertical. So that I just included it as I replaced all the y's with x and made it y.
So that's actually, it's not bad. The only caution, this one was a pretty simple graph. If the graphs get a little more complicated, it can be difficult to figure out which one's on top and bottom. That's the only thing. But otherwise, that's fine what you did. The other thing, just this has nothing useful in this problem, but since I got it here, occasionally, like let's say you're doing this reality check. You put the equations from number 1 in. Oh, yeah, you can. You put the equations for number 1 in, and you have those. Is it whole again? Yay! Thanks. You can just leave it right there by the door.
Just any one you want.
Yep, that was it. Thank you. And then if you want to go on, like maybe you're like, I know I might want to come back and do number 1, so you don't want to have to retype those equations in, but you don't want them to get in the way when you do number 2. You can turn off equations on the calculator. So if you notice right now on both of those, the equal sign is highlighted. If I move my cursor, if I can get it over there, come on. If I move my cursor on top of one of the equal signs and then just hit enter, it's no longer highlighted. So when I graph, it's not going to graph it. I've turned off that function. So that's something you can do if you ever find it useful. Any other questions on that? All right. The last one, that is the last one. So, yeah. All right. Oh my God, it's going to be so much fun what we do today. Actually, I'm going to warn you, it's just hard to visualize. So, let's try to get our focusing brains on. Oh, you have to do alpha. And then now we get y equals. Right? Y equals is still going to change. And now we hit this button. All right. Well, no, I'll have people do that at the end. All right. Volume by cross section. So now we're going to look at 3-dimensional solids. And this is why it gets a little tricky to visualize. And I apologize, I'm not the best artist either. So we'll do our best, though. Let's just see. Before we do volume by cross section, though, let's talk about prisms. So by definition, and actually, I mean, specifically we're talking about right prisms, but we'll just call them prisms. By definition, what a prism is, it's a 3-dimensional object, and it has 2 parallel, congruent polygonal faces. So, for instance, we could have a triangular prism. Here's the top of the prism, this triangle. The bottom of the prism has to be a congruent and parallel triangle. So I'm going to make these 2 edges dotted because they're going to be in the back of this prism. So there's my 2 congruent polygonal bases. Oops, I don't want that one dotted. And then if I just connect these, there's my triangular prism. So we name the prism by the shape of the face. we could have a hexagonal prism. This is going to be the only other like specific kind of prism that we draw, but I'm going to make like a flattened out hexagon because we're looking at it from an angle. Try to give it that 3D perspective. Like I said, I'm not the best at drawing these things. And then at the bottom, I'm going to do the same, try to draw the same one. And then we connect. Oh, that's not so great, but there we go. There's my fabulous hexagonal prism. Not. And we could keep going with this, but I think we get the gist. These I've been using the word, but these congruent faces, they are actually called the bases of the prism. If you did a whole like separate course in geometry, you may have like already learned all this, but since we don't do a separate course in geometry anymore, I'm going over it with you guys. So that's a base, that's a base. We're used to base being the bottom, but in geometry, base doesn't always mean the bottom. In this case, it means the top and the bottom. But I could also take these prisms and turn them on their side, and then the bases are on the sides. So that's why we define them differently. And again, over here on the triangular prism, it's the top and the bottom that are the bases. And then the distance between the bases is called the height of the prism. And again, we're used to height being how tall the thing is. But if we turned a prism on its side, now the height would be going sideways because the distance between the bases would be measured horizontally. So the height is always the distance between the bases. This actually works for, it's not technically a prism anymore, but a cylinder. A cylinder basically acts like a prism with an infinite number of edges on the polygons. But we still have these two bases. And then we still have the height. So, the reason I bring all of this up is we're going to be taking our solid, whatever solid we're actually trying to find the volume of. Just like when we were finding area, one way we did it was we sliced it up into rectangles. Now we're going to be taking our solid and slicing it up into these prisms. So the volume of a prism, so now I'm writing at the top of the screen if you can't see. The volume for any prism, no matter if it's a triangular prism, a hexagonal prism, even a cylinder, if we're going to consider prisms in this case, so even if it has rounded bases, the volume of any prism can always be found. Actually, does anybody know? Trey? Yeah, and I'm going to be a little more specific. Area of the base times the height. And so when we're in geometry, a traditional notation is when we're talking anything related to the base, we use a capital B. So make sure you make a capital B there, but a little h. But I'll define the capital B is the area of the base. Actually, I'll say a base because we only need to find the area of one. The area of a base, and h is the height of the prism. And we can see that with the cylinder. I mean, it's still area of the base times the height, but this time the base is a circle. What's the formula for the area of a circle? Pi r squared. So if you happen to remember the formula for the volume of a cylinder, it's pi r squared h. because it's still area of the base times the height. Okay, so any questions about that? All right, don't worry if you're having flashbacks. I know the IM, I forget now if it's IM 1 or 2, where the apothem, I never know if it's apothem or apothem. I always forget. But you remember having to do that, and you had to find the area of the triangles, and then it's like, ah! Don't worry, we're not doing any of that. So if you're having flashbacks to that, it's okay. Don't worry. Oh, we're going to have more fun than that. No, actually, I don't think it's as bad as that. All right, so now let's look at our figures. So I'm going to, just for ease of drawing, I'm going to draw another cylinder here. But this is kind of, I'm going to put a little squiggly line here. But we're going to extend this idea to things that aren't cylinders. So we're just going to start off with this, though. We do already have that formula for the volume of a cylinder. But in general, another way, because what if we don't have, like our shape is just some wonky shape, which we're going to see wonky shapes now. We can, like I said, slice them up into cross sections. So let me display my artistic prowess, which is not very good. I'm going to go ahead and draw a cross section here. Think of this like a cake, and I was going to slice the cake just all the way across, though. So I slice it like this. Now the cross section would be, if I could pull those two pieces of cake apart and show them to you, that shape of that cross section, well, that's the cross section. But we're going to make the cross section have some thickness. Again, just like we did before with rectangles in the area where we cut it into rectangles. So imagine that there's a little bit of thickness to this. This is where the picture starts falling apart because I'm not very good. So there's the cross section right there. Now, to give you a little preview, I've got this picture right here. So this is no shape and they're probably, I mean, there's so many wonky names for things. This might have a name. But if you take a look at this, the base of the solid, the piece of paper, I don't know if you can tell, but it's a parabola. And then these cross sections are all semicircles. And so it makes this kind of holistic shape here. These would be all the cross sections that we're going to cut this shape into. We're actually going to find what our first problem is. We're going to find this volume. I'm going to show you how to do it. But these represent all the cross sections here. So imagine taking this cylinder and cutting it up into all these cross sections. I can't draw all of them. It's easier just to draw this one. So, but if we could have all of these different cross sections stacked next to each other and filling it up, we could find the volume of the cylinder that way. So the volume could be the sum of the volume of the cross sections. I'm going to stop there and see if there's any questions on that idea. Does it make sense what I'm trying to do here? And please ask if it doesn't. Well, so volume. Actually, I need to specify because we got all these different volumes. So I'm talking volume of the cylinder. Which, how about we'll just call V sub C. That way we don't have to keep writing it out every time. So V sub C is the volume of the cylinder. So the volume of the cylinder is the sum. Oh, look at that. We have a symbol for sum of the volume of the cross sections. I'll do V sub C for the cross sections. But we know from up above, because these cross sections are basically very thin prisms on their side. So the volume of the cylinder is the sum, and then instead of saying volume of the cross sections, let's say area of the base times the height of the cross section. I'll just leave it like that though. So let's go back to our picture for a second. The area of a base of the cross section. Now in this case, in my picture here, it's a rectangle, but depending on what your shape is, your cross section could be any shape. It could be in the model I have there, they're semicircles. They could be triangles. They could be parabolas. They could be all sorts of different things. So in general, the area of our cross section, we're going to represent it with a function. And in this case, I'll call it A of X. I'll show you how to find that A of X. But in general, it's going to be some function. And then the height of the prism is the thickness in this case, because I put it on its side and I've made it really thin. And that thickness is going to correspond to our change in the X values. It's our delta X that we've seen before. So then going back to my sigma, the volume for a cross section is the sum. Well, instead of area of the base, I'm going to write A of X. And instead of height, we're representing that with delta X. And then through the magic of Riemann sums, which don't worry, I'm not going to make you go through the whole Riemann sum process again. But if you recall, you may not, because it's been a while, but the definition of a definite integral is a Riemann sum. And so we can turn this, there's steps in between, which like I said, I won't bother getting us into, but it's a Riemann sum. We can eventually turn this into an integral A of X, and then our delta X is what becomes the dx. And then I'm just going to put limits A to B. I'll show you how to find the limits. And there it is. So the integrand, when we're finding volume by cross-section, the integrand is all based on the area of the cross-section. That's where most of the work is going to be, is finding the area of the cross-section. Once you got that, it's easy enough to fill out the integral. And then depending on the integral, some integrals, as you know, are easy to evaluate and some aren't. So just depends. So, any questions on that? So let's put this in a cloud. It needs a cloud. So, I'll use this color. Volume by cross-section. And I won't make it a wordy cloud, don't worry. Sometimes these are going to have to be dx problems, and some of these are going to have to be dy problems. And on these, we don't have a choice. I'll show you how to find it. So I am going to give you two different integrals. It's either the integral from a to b of a of x dx, if it's a dx problem, or I'll say the integral from c to d of a of y dy if it's a dy problem. Guess I'll move it up so it's high. You see the problem there. But I do want to write one more thing before I put a cloud. The way that you can tell if it's a dx or dy problem, dx problem is if the cross sections are perpendicular to the x-axis. Dy problem is if the cross sections... Hi! Oh, come on in. Perpendicular to the y-axis. Hi. So, and we're going to, actually, I've got a dx and a dy problem, so you'll be able to see it. So any questions about that? All right. Go ahead and write down the problem then below, because that's what we're going to solve. And that's the one with our cool little model. I don't know if it matters. They replaced that bulb with something different. Well, it actually, in the beginning when I first moved in, it was the same lights, and but it was still the emergency light, but it started flashing after the buildings were first remodeled, and so they replaced it, but they didn't have the right bulb, and they never changed it out. So I don't know if that matters.
Yeah. Okay, that's what happened.
Okay.
Thank you.
Yeah. All right. Anybody need the cloud? Or I'll scroll up all the way then. So just like before, we're going to have to draw the picture. Draw the picture. Always draw the picture. Step 1, draw the picture. Supposedly they're going to replace the lights with LED lights, but I hope we can still dim them. Yes.
How would you know if the cross sections are perpendicular?
The problem's going to have to tell you like this does. So, yeah, it'll be easy. All right, let's draw the picture. This isn't that bad a picture to draw. I'll put my axes here. X equals y squared, sideways parabola that opens to the right, but the origin is just right there. Oh, let me change colors. Right there, the vertex at the origin. So this is x equals y squared, and then x equals 4 is just going to be that vertical line. So the base of the solid is the region bounded by these two. So we can see that this region here is the base of the solid. So then it says cross sections perpendicular to the x-axis are semicircles. So like I said, that's exactly what I have here. So the cross sections are semicircles. Now, how do you draw this on your paper? I mean, some of you guys might be able to. Don't take the time to do this, though. What we do need to worry about, though, is one cross section. And it doesn't even have to look really great. Like, you'll see what I do. But what I'm going to draw on my paper will look nothing like this. But I know for some people it does help if you visualize it. Like, honestly, you can solve these problems without being able to know what the shape actually ends up looking like. So it's okay if so some people are very visual and some people are like, they read this and go, I know what it looks like. And some people are like, I have no idea what it looks like. And it doesn't matter if you don't know what it looks like. But I did just want to give you an idea of this. So here's all you need to do, though. So it does say perpendicular to the x-axis. And like Sufra asked, like, how do you know? It's going to tell you. It's going to tell you the cross sections are perpendicular to whichever axis. This says perpendicular to the x-axis. So I know that these cross sections are going to cut my solid vertically. So I put my representative rectangle vertically. And it should go across the entire region. And then you can see the thickness of the rectangle is along the x-axis, so it is a dx problem. And then to draw the semicircle, I literally just draw a semicircle on top of that. That picture that I just drew looks nothing like the object, the model that I was showing you. But that's literally all I do. And that's fine. Like you can solve the problem with just this. So we know that the volume is going to be the integral of the area of the cross section, dx. Like that's the formula. Like I said, it's just all about finding the formula for the area of a cross section. By the way, what will my limits of integration be? Yoj?
0 to 4.
Yeah. It's a dx problem, so look along the x-axis. The shaded region goes from 0 to 4 and the x values. That's how you know. All right, so we have to find the area of the cross section. Do this work to the side. Area A of x. We know it's a dx problem. I'm going to put dx there to remind me. So these are semicircles. What's the formula for the area of a semicircle? Pi r squared divided by 2. Just start off with that. Pi r squared divided by 2. So the variable in this is the r. We need to find something to represent r. So go to your picture. Where is r in this picture? Super. The height of what? We have like a lot of stuff.
So the semicircle vertical to the height.
Oh, yeah. It'll be easier to point on this. You could look at, so if I understand right, you're talking about this. Yeah, so on this height of the semicircle does represent the radius. That is true. I didn't think about that. That's going to be very hard to work with. But you are right. Where is there another place that the radius appears in this picture, though? Maddie's got a hand up?
Yeah, it's between the curve and the x-axis.
Yeah. So let me be more specific. What's going to help on these, whatever your variable is in the formula for area, see where that is in your representative rectangle. That's one of the important reasons why we draw it. So I'm going to put the radius right here where Maddie said. And the reason why that one's going to be the more useful place to look at it is now we're going to look, let me move this down so I can point. Now we're going to look at this distance, but now this distance is between curves that we know. This is the parabola, this is the x-axis. And it goes top minus bottom, it's going vertically. So we're going to go top minus bottom. However, not a big however in this case. Anybody know? That's a very vague question. Anybody know my however, where I'm going? What is the top function? X equals y squared. Except that's not really a function technically in this case, but the top curve I should have said. Top curve is x equals y squared. What do I have to do with that?
So it's based on x.
So it's based on x. That's the key. Remember, it's a dx problem. So I just have to make sure my equations are solved for y. So x equals y squared or y equals plus or minus x. So the radius is the positive square root of x minus 0 or just square root of x. And then I put it into my formula for the area. So that means area is just pi, well, root x squared is just x over 2. Now I have the formula for the area of the cross section in terms of x. So again, what we did, we knew the cross sections were semicircles, so we found the equation for a semicircle, just in general. The variable in that was r, so we had to be able to write r in terms of x, because this was a dx problem. And then we plugged it in. Any questions about that? Because now, we're ready to go back to our integral. So the volume is from 0 to 4, the integral from 0 to 4 of pi x over 2 dx. And now we're on the home stretch. So, any questions how I got to that integral? I know you may be thinking, I kind of get it, I think, but actually let me ask this. Give me a thumbs up if you're at this place. Like thumbs straight up means that you are, I think I kind of get what you did, but I don't think I could do it on my own. And if you're not there, like where do you think you are? Okay, cool. I see a lot of straight thumbs up. That's fine. This is weird. We're going to do another example, and hopefully I can get you to the point with a second example of, okay, I'm feeling a little better, but I'm still not quite sure. At that point, it's just going to be you guys practicing them on your own. But let's go ahead and finish out this integral. This isn't so bad. I'm going to factor out the pi over 2. So the integral is just x dx. You guys keep going. I won't talk my way through it, but I won't pause the screen. You guys keep doing it on your own, though. Any questions? Yes, super.
Do you need to put units after the whole time?
No. Yeah, if you didn't hear the question, do you have to put units? No, you don't have to. All right. Anybody still need this? We're going to do one more example together. This is actually one of my favorite units because I actually do love all the volume stuff. We're going to do more volumes. It's really cool. It's so cool. All right, let's try this one. You may think I'm crazy, but, you know, it's probably true. Cool hair! Sorry. Need some water? Okay. Was it just me, or did people have trouble waking up this morning? I had a lot of trouble. This morning I was like in a super deep, like, dream. I don't even remember what the dream was now, but I just remember waking up like, wow. It was one of those, I mean, usually I wake up actually really easily, but this one, it was one of those where the alarm is in my dream before I realize it's the real alarm. What's the first thing you think we're going to do? Draw a picture, that's right. Well, at least they're both straight lines. Eh? All right, 1 minus x over 2. It's a line with a negative slope. It's going to cross the y-axis at 1. I'll just put 1 up there. It's going to cross the x-axis at 2. I don't remember, I said you don't have to make these super accurate, but when it's simple like this, I like to. So that's y equals f of x. G of x, see that has a y-intercept of -1. Still going to cross the x-axis at 2 though. It's going to be this line. I did really space this out though because it really does help if you make your pictures big enough to draw inside. You don't have to make it as big as I did, but even if this wasn't notes, I'd be making my picture pretty big. Okay, this time cross sections are perpendicular to the y-axis. So which way do I draw my rectangle? Yeah, horizontally. You can draw it anywhere in the picture. I'm just going to draw it here. So there's the bottom of the triangle, and I'm just going to draw a triangle here. That's supposed to be my equilateral triangle. That would actually be kind of a cool looking shape. Maybe I'll try to make a model for that, because that would be cool. Anyway, we got that. Any questions about the picture? So the problem was nice enough to give us this equation. I don't expect you to have the area of an equilateral triangle memorized, so that's okay. Don't worry about that. Area of a cross section. By the way, is this a dx or a dy problem? dy. I'm going to write dy, visual over there. Remind myself, I got to put these all in terms of y then. So the area is given as s squared root 3 over 4. Now, it didn't define what the s is. What do you think the s stands for? Side. So where would I label the side on my picture? Where would be the useful place? Yeah, I see people drawing horizontally. In relation to the representative rectangle, it is the length of the representative rectangle. It's the entire side of the triangle. So we need to find the length of the side of the triangle. Now this time the triangle is going horizontally, so we're going to think right minus left. So is it always the same function on the right? Damn it! It is not! Yes. Yes, we can. Very nice. In this case, because there's nice symmetry to the problem, let's just worry about the top part. And then we can double it to get the entire volume, because the problem will be totally symmetrical throughout. And that way we can only worry about one integral, one right function. So we're just going to worry about this guy. And double it. Excellent. But I do have to rewrite that function in terms of y. So right now, for y equals g of x, oh, sorry, that's f of x. y equals f of x, we have y equals 1 minus x over 2. I'm just going to solve that for x. I'll multiply everything by 2. And x equals 2 minus 2y. And that turns out to be side then. The side of the triangle can be represented. Right is 2 minus 2y, left is just 0, so the side is just 2 minus 2y. Now, honestly, I still like to, I don't know what's going to happen with this one, but I still, before I go into the integral, I like to still play around with the area formula. I mean, I've got everything I need. I can just plug this into S, but maybe I'll be able to, like, factor some stuff out, simplify some stuff. I don't know. I play around with it still and get it as simple as I can before I put it in the integral. That's just a personal preference, though. But let's see what we can do with this guy. So the side is 2 minus 2y squared, root 3 over 4. This kind of just depends on what you're going to do to solve the integral. Because you could leave it like that and do u substitution. And it wouldn't be that hard. But you could also square it all out if you wanted to. And again, I'd say that's personal preference. One thing I can do, though. Anybody see one thing I can do? Trey? Yeah. So if I factor out a 2, see, it would simplify. What do you guys think? Silver? Oh. Very good. Yeah. Just be careful when you factor out the 2, because the whole thing was squared. That 2 is still squared. And actually, that's kind of nice, because then area is just root 3. The 2 squared on top cancels out with the 4 on the bottom, so it's just root 3 times 1 minus y squared. Oh, it just looks nicer. So that's what I mean. I like to play around with the formula for area, because a lot of times you can just make it look a little easier to work with. Sometimes it actually is easier to work with. This one just looks easier. It's not really easier. So now I'm ready. We're ready to find the volume. Any questions so far? Yes, David. Because technically I was just trying to show right minus left. And so for the length of this rectangle, which represents the side, the right function is the line, but the left function is 0. But yeah, you didn't have to do that. Alrighty, so what are my limits of integration going to be? I think I heard it. I heard it over here. Was there somebody that said it? Maybe I just wishful thinking. Rena. 0 to 1. Yeah. Remember, it's a dy problem. So make sure you're looking on the y-axis. 0 to 1. And then the area. I'll factor out the root 3 right now. And we get that. Is this going to be the volume? Yoj? Right. Oops. I didn't give myself. I was going to divide by 2, and I left myself room for that. I was thinking along those. Yeah, it's going to be 2 times this. Remember, we're only doing the top part, so then we have to double it. And then we'll solve it. Any questions there? All right, I'm going to freeze the screen, pause the video. You guys try working that out. and we will check in. Alrighty. Whoop, wrong button. But there it is. There you go. Did I screw up? I'm looking at faces. I chose to just use... This was a simple enough one. I mean, you could do like formal U substitution, but the derivative of the inside is just a -1, which I didn't have, so I just put a negative here. Think about taking the derivative here. 3 times 1/3 cancels out, and then you decrease this by 1. You get squared. But then you would have to multiply by the derivative of the inside, which is negative, so it just cancels out with that negative. But you could have, I mean, this isn't a hard one to square, so you could have just squared it. You could have done U substitution. Yes, Trey? Say that again?
You multiply by the 1/3 on the 2, 3, but also on the 1 side.
Oh! Where'd I get that 1/3 from? I don't know, actually, if that's what I was thinking. That should just be a 1. Thank you. My brain was just, yeah. Does that look better? Okay, shoot. Just seeing if you guys are paying attention. Good job. It's my story, and I'm sticking with it. Anyway, any questions? So that's going to be your homework for tonight. Just having fun with volumes by cross-section. Yeah! That's the end. I'm going to end the video now.